Good evening and welcome to JDA News. Today we will be broadcasting a live feed for the Spring 2018 Dynamics Project 2 competition. Students at the University of Delaware have entered an Impulse and Momentum competition. If they answer their complex problem correctly, they will be the recipients of an $1,000 cash prize. Let's listen to them talk through their problem. The students were given the following variables. The moment of inertia at A is 0.02 kilogram meter squared. Inertia at B is 0.036 kilogram meter square, and moment of inertia at C is 0.032 kilogram meter square. The system is starting at rest. The radius of A is 0.1 meters. The radius of B, outer, is 0.2 meters. The radius of B, inner, is 0.1 meters, and the radius of C is 0.2 meters. The moment at A is 2 Newton meters. In addition, they are assuming that the belts do not slip.
Okay, for this dynamics problem, we're going to solve it by using the method of angular momentum and impulse. Here we have our equation of angular momentum and impulse. We have our angular momentum of state 1 plus our impulse is equal to the angular momentum of state 2. To start off, we drew our free body diagram of pulley A with our tensions and our constant moment of 2 Newton meters. To solve for this, we plugged all of our info into our equation up here. As you can see, the pulley started at rest, so the angular momentum of state 1 is 0. And we have our moment of 2 Newton meters from 0 to 2 seconds. Our change in our tensions, and that is equal to our mass moment of inertia of pulley A times the angular acceleration in state 2. And solving for delta TA, here we get our first equation. Moving on to pulley B, we have our free body diagram here. Again, the same thing, we took all of our known information, plugged it into our impulse momentum equation, and that gave us equation 2 with our 3 unknowns, TB and TA, and angular velocity of B. And for pulley C, we have our free body diagram here with our tensions and radius. Again, we have 0 for our state 1 of our momentum, have our impulse, the radius times the integral of delta TB is equal to our 0.32 times angular velocity at C in state 2, which gives us equation 3. And as you can see here, we have 3 equations, 5 unknowns, so we still need a few more equations to solve this problem.
Okay, so the second step in solving this problem is using the assumption that the belts at the pulleys do not slip. Using this condition, we could relate the velocity at A and B outer, and as well as B inner with C. So velocity is equal to radius times angular acceleration. So here we plug in the value of the radius, and we have omega A is equal to 2 times omega B is equal to 2 times omega C, and plugging in equation 4 and 5, we got 2A is equal to 4 times omega C. So now that we have 3 additional equations, in addition to the equation solved in the first step, we can plug in equations 1, 3, 4, 5, and 6 into equation 2, and we got this simplified, and we could solve for omega C, which is 79.62 radians per second. Using the relationship that 1 revolution is equal to 2 pi, we get that the number of revolutions completed in 2 seconds is 12.2 revolutions.
It looks like we have a winner. Can I get a drum roll, please? Group 9, please come forward. Woohoo! Woo! Here's your award of $1,000.
Thank you.
Yay.